So let us look at a very popular and simple convolution neural network called LeNet. It was actually created by Jan LeCun, one of the most popular figures who came up with the whole idea of convolutions in deep networks. And this paper was actually published in 1998. Here is a very interesting story. Even though the convolution neural network idea, right, was published and researched fairly thoroughly in the late 1990s, it didn't become popular till almost 2012. The reason being, the fundamental reason being, even though some of these ideas were present there, we did not have large data sets or GPUs for that matter. Remember, the whole popularity of deep learning, some of these concepts are almost, they have been there since late 1990s. But why did it take almost 15 years for these techniques to become popular? Even though the theory behind some of these concepts are already present. It's because we didn't have large data sets to train deep convolution neural networks. Similarly, we didn't have GPUs. Lots of compute was required. And remember, in late 1998, right, a lot of people lost faith. They lost faith in neural networks because neural networks didn't work very well because of the failures of neural networks in late 90. Even though they became popular in late 1980s. By the time you came to late 90s, the more popular algorithms were SVMs, and SVM was the most popular algorithm of the 90s, literally. Tons and tons of research work. So because SVMs were so popular, everybody took notice of SVMs, but people didn't really care about LeNet. There were only a very small group of researchers like Jan LeCun, Jeff Hinton, etc., who were struggling to publish their research work in late 90s because people said, does this really matter anymore? It's only, and their day actually came in 2012. So in research, what often happens is you may have the most brilliant idea, but the timing is not right. And unfortunately, because you don't have large data sets or large GPUs, you've not been able to prove the full potential of your algorithm. And that has happened to some of the most brilliant minds in computer science, for that matter, even in machine learning. And Jan LeCun is one such guy. He now teaches at New York University, and he also heads Facebook's AI Research Center in New York. Okay, so let's go and understand. This is one architecture of LeNet. There are multiple slight differentiated architectures, but I'll explain this. The input image is a 32 by 32 grayscale image. Okay, remember this was in late 90s. We didn't have computational power, so people even didn't think of color images and RGB images at all. They were thinking of small images, and the task they were looking at was your MNIST task, literally. They were looking at MNIST task of detecting handwritten characters. Okay, and the architecture is very interesting. The first layer is convolutions. Okay, and you had, they call it feature maps here. Feature maps basically means kernels. And the C here says that it is convolution layer, right? And we have 6 kernels here, and the output size is 28 by 28. The kernel size here is 5 by 5. Okay, they didn't have padding and all of those concepts. The reason I'll provide you a reference link to this URL. It's a very good URL. The reason I'm showing this example here and not in the research paper itself is because each of the layers architecture is very neatly explained here. So for example, here he says the kernel size is 5 by 5 and the activation unit is sigmoid. Remember in 1998, they didn't have ReLU, right? So it's very, very neatly explained what each of the convolution layers is in simple to understand terminology here. That's why I'm pointing you to this reference link, and that's why I'm using this reference link. Okay, so you can read this reference link at your own leisure and go through some of the details. I'll explain you some of the details here, right? So the kernel they are using is 5 cross 5. This is a grayscale image, and they have 6 such kernels here. So you see 1, 2, see gray, black, gray, black, gray, black. There are 6 here. So this tensor is of size 28 cross 28 cross 6. Okay, and you have 5 cross 5 kernels, and you have 6 such kernels here. Okay, there is no padding, nothing here. Okay, that's it. That's obvious, right? You have 32 plus 5, 32 minus 5 plus 1. 32 minus 5 plus 1. Okay, 32 minus 5 plus 1 is 28. That's the size of your images here. So first layer is convolution. The second layer, they call it subsampling. And remember, the activation units here are sigmoid. They are not ReLU, because ReLU was not even invented then in 1998. People were still playing with sigmoid and all the problems that sigmoid has. But still, they got this to work. Today, we don't use sigmoids anymore. We use ReLUs. okay, because we are in 2018 now. The second stage is called subsampling, which is nothing but your mean pooling, literally. Subsampling basically means mean pooling. What do we do in mean pooling? We take 4 pixels and we take the average of them and generate 1 pixel here, right? That's what we're doing in mean pooling. That's what they do. They have a 28, each of these images is 28 by 28. They do a mean pooling with a pool size of 2. So every 2 by 2 here becomes 1 pixel, as a diagram shows, right? Every 2 by 2 pixel here becomes a 1 cross 1 pixel. So now what you have here is a tensor which is of size 14 cross 14 cross 6, because you have 28 by 28, you have halved it, right? So you get 14 by 14 here, and you have the same six maps that you have, or 6 kernels that you have. So at this stage you have, so this is a convolution stage, this is a sampling stage. Sampling is nothing but average pooling or mean pooling, right? Next you do again convolution. Okay, so you're done with sampling. So these two, this is convolution, this is pooling or sampling. Then again you do convolution. This time what do? Again you do convolution with 5 by 5 kernels, and you do 16 such convolutions. You have 14 cross 14 values here, right? You have 14 cross 14 values, and you have a channel depth of 6, because there are 6 values here. This tensor itself is 14 by 14 by 6. So to go from here to here, you do 5 cross 5 cross 6. So each of your kernel is 5 cross 5 cross 6, because the data here is a 3D tensor, not a 2D matrix, right? So this depth 6 should be same as the kernel value here. And you have 16 search kernels. So what you get here after convolution is a 16, 10 cross 10 cross 16. Again you do sampling, right? The next stage, see, you've done convolution first, sampling, convolution. Again we are doing sampling to go from this stage to this stage. And we are doing sampling, which is nothing but mean pooling with a size of 2. So what you have 10 cross 10 here, the 16 remains the 16, the 10 cross 10 becomes 5 by 5, because you're doing a mean pooling of 2, right? So what do you have here? You have 16, you have 5 cross 5 cross 16 here at this stage. Then the next stage is again a convolution stage. Because I have 5 by 5 here, my kernels are also 5 by 5 size, right? And I have a depth of 16. So my kernels are 5 cross 5 cross 16, right? And I have 120 search kernels. So what do I get finally? I get simply a vector of size 120 here. I get a vector of size 120. Now from here to the next level, I will just do a fully connected layer. Remember, there were no ReLUs then. So this fully connected layer was a sigmoid layer. Then the final layer is my softmax layer. Okay, so let's look at it again. This is my input image. I do convolutions, I do mean sampling, again convolutions, again mean sampling, again convolution, then I do a fully connected layer, then my output layer, which is my softmax. And the task here, because it has 10 units, because you're trying to detect whether it is 0, 1, 2, it's a 10 class classifier, right, MNIST. Okay, remember, very, very importantly, in 98, they were only using sigmoid. They didn't have all the complex variations that we have now. They didn't have ReLU. And they were mostly using gradient descent. They didn't have all the advanced algorithms like ADAM, ADAGRAD, etc. Right? Even this was a fairly big deal in those days, even on grayscale images. Of course, today we have way more complex, way more complex. Let's look at how many layers we have. We have 1 layer here, 2nd layer here, literally like 4 or 5 layers, that's it. Not a big deal, not a very deep network. But it worked very, very well in the late 90s for simple tasks like MNIST. I want to show you, because we have learned about convolutions, we have learned about max pooling, mean pooling, etc. This is the whole structure. This is a slightly old network, but still a very powerful, good network to learn. And I recommend you go through this blog where each of the layers is very neatly explained. Like what is the kernel size, what is the activation unit, right? Very neatly explained. Even though I've explained it here, it's good to recap all of that here. Very nicely explained blog. Okay, sounds good. So since we've seen LeNet, we'll learn some more concepts which are important for convolutional neural networks and move on to very complex, state-of-the-art 2012, 2015, 2016 papers and research work. Very recent research work. Very exciting work.